Hey, sixth grade. Some of us, I think, were not here on Monday or Tuesday. And I think there's also been a little bit of sort of prevailing confusion over claim, evidence, and reasoning. So I thought I would use this opportunity to review that with everyone using this video. So right now, what I have up on my screen is first hour's Google Classroom. Obviously, your class may not be first hour, but it will look similar to what we're doing here. I'm going to direct you, if you have not finished Google, or if you've not finished Explore 2, that you go to the classwork tab. And you're looking to go to the bottom of Earth's Materials, Systems, and Natural Hazards, which is right here. All right, so I'm going to open this up. And inside, you're going to notice there's a whole bunch of things that are attached to this. We have the actual Explore activity. Yours will have your name on it. And there's a slideshow. Now, this is the same slideshow that appears up here under slideshows. Okay, so it's not something different. It's the same one. This is the slideshow that we used in class that day. There's also two videos attached here, and these two videos are actually embedded in the slideshow. So the only reason why you need to open these is if you just want to watch these by themselves for some reason. For convenience, though, all you need to do is open up your assignment and open up your slideshow. Now notice that even though this is an Explorer, we're not going to STEM scopes this time. This is the only time I have done this year, so it may be a little confusing. But the actual Explore activity in STEM scopes is quite long. And as you may know, we are still in the middle of finishing up the rock cycle. So rather than double you up, we did this one as just sort of an in-class activity. But it's a good opportunity to talk again about claim and evidence and reasoning and review what's needed there. So before we really get to the CER, so I'm actually not going to really get into this just yet, because a CER is supposed to be something that you write after you've done some kind of investigation. And it could be a research situation where you're doing research, or it could be an experiment, or it could just be, on a test. What it'll be is you reading through a scenario and some data and then making a claim. So we're going to set this aside for just a minute, and I just want to review what we talked about in class on Monday and Tuesday. Now, I'm not going to go into the same kind of detail that I did on Monday and Tuesday with the class. So if you missed class that day, please make sure that you go here to the notebook thing, get your notebook, your notes for the day out, and that you go through the slideshow and fill in the notes, because that is going to help you. That will not just help you with this particular activity, but it will also really help with the rock cycle. Several questions in the rock cycle ask about whether the change that you're observing is a physical or chemical change. So it's important that you understand that using these notes. And again, I'm not going to be taking a ton of time on that for here. So, but I am going to come here and go to the slides. Yeah, super cool glasses I've got on there. All right, so I'm going to put this in presenter view just because I personally don't like to have all this clutter around it. You obviously don't have to do that, but for me, this is much cleaner and easier to see. So again, we started out this part of the unit talking about the rock cycle. So we went through a little bit about sedimentary and metamorphic rock, and then we really spent today focused on igneous. The igneous rock is key. I'm going to click through our normal beginning of class slides because it's kind of, in some ways, the origin of where the rocks are coming from. It's when rocks go from being in a molten state of magma to actually being what we think of as rocks. So it's really, it happens in two very distinct ways that we'll talk about in just a second. We started out here looking at, this is obviously Minecraft blocks. This is not how they look in real life. And I'm not pretending that they are. But I do think that Mojang, when they programmed Minecraft, did a really great job, because these three stones, this is obsidian. Hopefully you recognize that if you're a Minecraft player. This gray one is called diorite. And then the one here on the right is called granite. And each of these are igneous rocks, but they form under different conditions. And if you play the game, you probably know that you make obsidian by combining water and lava, which is great because that really is kind of how obsidian forms. Obsidian is what we call a volcanic igneous rock, which means that it only forms from lava, which has been shot out of a volcano, and usually in a very cold environment. So this is one that it like basically sort of freezes before it has a chance to form any crystals or do anything else. So it's kind of special. It's super cool to play with in real life. It's got it's just basically chunks of black glass, but it's interesting. Diorite and granite are both formed other ways by, in other processes, which we'll talk about. But if you do play Minecraft, you probably know where you find these, and where you find these in Minecraft is also where you would find them in real life. So it's interesting. Um, this is where you're going to get your definitions of the difference between a physical and a chemical change. Physical change just means that we're not forming a new substance. A chemical change means that we are. Physical changes are anytime you're just changing in size or you're cementing things together. And even to a certain extent, metamorphosis, where you're squeezing them, where you might fold rock. If you take limestone, and I realize that folding rock isn't something that's easy to think about, but if you put enough pressure for enough time, they do fold kind of like cloth, or kind of more like fun foam, but it's still going to be the same kind of rock. It doesn't really change until you either have some kind of chemical acting on it, like we had with the vinegar. And what was happening there was the vinegar was interacting with carbon and stuff on the surface, and it was changing that into carbon dioxide, which was released as the bubbles. There's also recrystallization after heating and cooling, which we're going to get into. This is what is most important for this CER we're going to talk about. Crystallizing is key. Okay. When water forms ice crystals and then melts again, that's actually not a chemical change. Even though water is making a huge transition in state, it's going from a solid to a liquid, or a liquid to a solid, or a solid to a gas. It's going to look very different as it makes that change, but it doesn't actually ever stop being water. The chemical composition does not change. So even if it's a pretty solid block of ice and has been for a while, it's still technically the same chemistry as the liquid water that comes out of your tap, or the rain that's falling, or the clouds in the atmosphere. So it's really key to remember that most state changes from solid to liquid to gas are physical changes. Rock is the only exception, and it's only an exception if it is melting in the presence of other minerals, other rocks. Because what will happen at those high temperatures is that the chemistry will rearrange itself and you will produce some new materials. So then it is a chemical change, because then the rock that results is different from the rock that melted. Now, that said, if you have a rock, if you have like a chunk of quartz and you melt it and you let it cool, that's a state change if it's by itself. This blending and chemical changing only happens if it's surrounded by other chemicals that might interact with it. So that's what happens in magma. There's all kinds of minerals and materials floating around in there. So there's tons of things that can blend. That is key, because that is how crystals form. Okay. And we also had a conversation in the past about this. You've seen this diagram before, I hope. We talked about this a lot last quarter when we talked about tectonic plates. So this is a diagram that shows subduction. That's what this is here. And in theory, this would be a plate like the Pacific plate, an ocean plate, hence the water over the top. Ocean plates tend to be smaller but denser than continent plates. Continent plates are more spongy and kind of thick. And because of that, when they run into each other, it is the continental plate that gets folded down into the mantle while the continental plate stays on top. We talked about that process a lot last quarter, but we didn't really talk a lot about the continent itself, like what happens to the continent. While this is getting melted down here, all we see is some, looks like it's on fire here. But what's really happening is that the continental crust is also, being shoved into something else. And that causes a lot of stress in this part of the plate, which causes it to crack and crumble, like you might expect of any rock being slammed into something else. And when that happens, those cracks create weak spots where magma can start seeping up. And that's why we usually have a lot of volcanoes along those subductive coasts. So the Rocky Mountains form this way. The mountains that go all down the coast of South America, the western coast of South America. Lots of volcanoes, lots of pushing because of there's magma being forced up from below. So igneous rock actually forms in two places, and this is key. All right, if it actually makes it to the surface, as it's doing here with this volcano, and then it runs everywhere. Okay, as it reaches the surface and it cools, that is a kind of igneous rock that we call volcanic igneous rock, of which obsidian is one. Okay, this environment is much, much cooler up here than it is down under the ground, because under the ground it's still warm from being close to the mantle. So this has a tendency to cool very quickly, and can be kind of dangerous, because it goes from being, this liquid to being a very heavy chunk of something. So that's one of the reasons why you really want to stay away. Plus, it's also very hot from volcanoes while they're erupting. The below ground, though, you see how there's all these little spots that they're showing that are gray, kind of look like speech bubbles from a cartoon. What that is meant to signify is that there's lots of places where magma will seep up, but it doesn't actually make it to the surface. And instead, it might melt some of the surrounding rock, but it will cool underground where it's a little bit warmer. And so what we notice then is that most of the igneous rock that we run into is actually forms this way. The stuff that actually makes it to the surface is comparatively rare. This is called plutonic igneous rock. That's not a term you have to remember for a test. But plutonic igneous rock is rock that, or intrusive igneous rock, is rock that cools underground in the bedrock. So our job with granite is to figure out, where does it form? Does it form above ground or below ground? And is the environment that it forms in warmer or cooler than other igneous rocks? So here's one way that we can think about this. This is showing crystallization. And when these igneous rocks forms, they often do form a lot of crystals. So the crystals in this case are kind of just like these little globs of a given mineral that are all stuck together. And if the globs are very small, the crystal is very small, you end up with something like gabbro here. So this gabbro sample that we're looking at here on the far right, notice that it is made of minerals called orthoclase, hornblende, and pyroxene. But it's hard to tell where one starts and the other stops. There's a couple of wider flecks that are probably the pyroxene, but the orthoclase and the hornblende are pretty contiguous. If you looked at it under a microscope, you'd be able to see little tiny crystals that are all making that up. But at a distance, it's kind of like looking at a pointillism painting. Everything looks like it blends together into one color. So these are very small crystals. Diorite here has some moderate sized crystals. So notice the diorite in real life looks very much like its Minecraft version. It has, kind of an overall gray appearance, but you can see these very distinct flecks of white and black and even some, distinctly gray chunks. These are medium-sized crystals by an igneous rock standard. And then this is granite. Okay, so I want to be clear here that this is one kind of granite. This granite, notice that this is also orthoclase and hornblende in the diorite. There's also orthoclase and hornblende in this granite. And that's why we make the comparison between these three, because they're made of approximately the same things with a couple of extra little minerals mixed in there. And yet they look very different because they have all formed in different environments. Granites, you can see very distinct white, very distinct black flecks, very distinct gray regions. It's clearly not all one color like labro. Okay, you have this very, very speckly, chunky look to it. Now, not all not all granite looks this color. It has quartz in it, and quartz can come in a lot of colors. In fact, amethyst is a quartz, and so is tiger's eye, and so is hawk's eye, cat's eye, all those variants. Of course, regular white quartz is a color too. So it is possible to have granite that's all kinds of different colors, and that's why it's such a nice decorative thing for things like kitchen countertops, bathroom sinks, that sort of thing. It also polishes really nice because it has that, this many crystals in it that can be reflective. So what we're going to talk about here, we're going to look really close at granite and talk about where it comes from. That's the claim that we're looking to make. So we're going to focus on this. And to help us do that, there is a video that I'm going to ask you to watch on your own, not right now. What this video will do is it will show you a chunk of Missouri granite, and that's why it's kind of a reddish color. The Missouri granite forms down by the St. Francis Mountains. So if you have been to Elephant Rock State Park or Johnson Shut-ins, all of that volcanic rock that's down, that plutonic rock that's down there is made of this kind of red granite that has been mined for a long time. In fact, Elephant Rock State Park is a quarry where they have taken it out and used it for different things and sold it. That quarry is closed now, and that's why we can go visit it, but it's a fascinating place to visit. But you'll see a lot of chunks of this kind of granite around there. So this shows you an up-close look at the crystals of granite and compares them with a diorite sample so that you can really see the difference in size. Okay. This is going to click us forward into the video, and I'm just going to try to move past it. Go on. So if you're looking at your slides, it'll play it for you. Okay. Then we're going to go from there. So that's one piece of information, is looking at the actual crystals that make up granite. This is the other one. It's looking at how crystals form. So this demonstration is one that we would have done in class. And, I know I keep bemoaning this, but this is one of those things that if I could just show you face to face, it's just really a very cool demonstration. The green bottle over here from Flynn Scientific is called, it has a chemical in it called phenyl salicylate. And it is kind of special because it melts at a temperature that's hot for us, but it's manageable. So we're thinking like the kind of weather you might be cooking something in. Okay, so not the temperature that you'd want to stick your hand in the water, but not so hot that it's going to pose an extreme danger to us. So if you take those crystals, and I put those crystals in the syringe that's shown here, and then I put it in some hot water on the stove, and it melts it down and it almost makes it look like water as well. In the meantime, then I also took these 3 bowls. So I have one pyrite bowl here that's full of ice, one that is empty, hence the normal, and then this one is full of hot water. Okay, and then there's a glass slide that has a C on it for cold, another one that says N for normal, and another one that says W for warm. So what I did here was I put the slide on the bowl, and then I put the bowl on my microscope, which is why the microscope is here, and then use the syringe to put 2 drops of the melted phenyl salicylate onto the slide, and use my microscope to film what happened. Now the film looks kind of golden color because of the lights that are in my office. It's actually a very white crystal that you're going to see. But on the next slide, um, there's a video that you can watch that will show you what the cold one did, what the normal one did, and what the warm one did. After you see the actual crystallization happen, then it's going to switch and show you the size of the crystals by just kind of going through and showing you in order how they looked and when they were completely crystallized. When you're looking at those, what you're looking for is how much white do you see? If you see a lot of white in it, it means the crystals are very tiny. That means you're seeing a lot of crystal edges and they're all refracting. So it makes it look like it's very white and hard to see through. If you see more distinct shards in it, that means that the crystals have formed much larger. Okay. And here's the video for that. Now, I would play that in this video, but that seems a little redundant. And it also seems like it's robbing you of the opportunity to really enjoy it. So I'm going to not. And if you want to pause the video here to open it on your own and watch it on your own, I highly recommend it because it's good for you to experience it. Plus, everyone who was there in class yesterday told me that it was great ASMR, which I think is weird because I thought ASMR had to have sound to it. This video does not. Okay, so go ahead and pause it here if you need to. Go to Google Classroom, watch the video for yourself. I will click on. All right. Now, hopefully you've come back after watching the video, and now we're ready to. Now we've done an investigation. Okay, we've observed some granite, making some observations of that, and we've observed a demonstration. We've done some observing of that. Now we're ready to look at the claim evidence reasoning. Now, I think one thing that bears mentioning is that claim evidence reasoning can be a little bit tricky because, in a way, we sort of do it inside out. We make the claim, which is kind of like drawing a conclusion, before we really state what we saw. And that goes to the order of the way these things are listed. Now, of course, we're human beings. We have control over our destiny. It makes it simpler to write the evidence statements first and then reason through it and then end with the claim, that's okay. All right. It's important that you understand, though, what the difference is between a claim and evidence and your reasoning. So that's one reason why I thought it was important to make this video. I'm going to call this up on my own here. And just a reminder of logistics, if you have trouble seeing this because it's so small, remember that Zoom is here. So you can go and zoom into 100%. If this stuff around it bothers you, you can also go to view and go to full screen and turn off the speaker notes so you have as much real estate as possible dedicated to your worksheet. Just missed that. Okay, so I have tried my best in this case to help you out with some prompts. One thing there's a couple of pitfalls that I'm really noticing with these that I thought it was important to mention. With the claim, what I notice is that sometimes we sort of skip the part where we read the directions and just plunge right on into claim because we don't know what to write. And so I've seen a lot of pretty random claims come through, like just random things that seem like they would be good things to assert. And I understand why that's happening, because this part right here doesn't really stand out, but it is important whenever you're doing a CER, especially in STEM scopes, that you look for this line underneath the title and read what exactly you're being asked to explain. Now, this one is asking you to answer a question effectively. They want to know where granite might be formed in nature. A lot of them are not asking a question. They are actually giving you your claim and saying, we need you to justify this based on what you've learned. So make sure you're reading your directions carefully and that you understand what's actually being asked. That's going to be key to getting a good grade on these. So that's number one. The second thing I have also found is that many people seem to want to write the whole answer in the claim. They're just answering the question in the claim completely. And then they get down to evidence and reasoning and they're not quite sure like they've already said it all. So there's nothing else to say down here. So that's why it might be helpful, rather than putting your claim right away, to start with the evidence, because that is where we start. We started by making some observations. So according to our experiment, and if you watch the video, you know this, okay? The crystals that formed in a warm environment formed more slowly and were larger than crystals formed in a cold environment. Okay, so if you watch that video, and hopefully you did, you would have seen that the cold weather drop of phenolsalicylate forms a really amazing array of crystals, but they're all very, very tiny. In the warm environment, it forms a really cool looking, it almost looks like a piles of shards of glass. You can really see very distinct triangular crystals there. So if they formed in a warm environment, they were formed slowly and they were large. In the granite observations that we made, what we observed in the granite was that the crystals that make up granite are much larger than crystals in other igneous rocks. Okay, so those are observations, and like I said, we're not even looking at the claim yet. Okay, we're just making these observations. Now we can start thinking through our reasoning now. All right, if granite, this tells me that granite had to have formed in a warm environment. The crystals are large, suggesting that it cooled slowly. Okay, so that's a reasoning. All right, I'm making a logical conclusion here. But one thing I do want to point out before I get too deep into the reasoning is that the evidence here, the statements, notice that I put according to our experiment and according to our observations of granite. That helps us to kind of shape what we're doing. But when you're faced with one of these, you're not going to have those prompts. And one thing I'm noticing a lot with our evidence statements is that we're giving things that we just know. We're just stating facts. That's not evidence. Okay, knowledge and evidence are two different things. What you know may be true, and you're very smart, so that's, it probably is true, but that's not what this is for. You need to show that down in the reasoning section. In the evidence, you need to be looking outside of your head at what information has been made available to you, and that's what you need to be writing about here. Now, in a case like this, where we're doing it as part of an activity, the evidence is going to need to be from something that we did as part of the activity. So in this case, we did an experiment, so I found evidence from the experiment. We also observed granite, so I have evidence from the granite. And don't be skimpy about this. If there were 3 parts, you should have 3 evidence statements. You should tell me evidence from each of the things we did. All right. Then I can go on down here and I can use my brain and show how smart I am down here. Okay. So that's what this is for. Having gone through now that I understand, I have my reasoning kind of mapped out, it's pretty easy now to say, well, based on what I've learned, then granite should form in places where the environment, helps if I spell right, warm. And probably magma is cooling underground. Okay. Now, I have introduced this thing here that is not really addressed here, but this is because this is where, again, I know from class that magma cools underground where it is closer to the mantle and therefore warmer than at the surface. Okay. So again, anything that comes from your brain needs to be down here. Anything, what goes here is stuff that you observed out in the environment, or it's something that you read in the data that's provided, or something outside of your head needs to be where this comes from. Okay, so if you want to turn it in with this text in it, that is completely fine. Also note that there is this second page here. Don't be confused by this. You're not asked to do anything on this page. The idea here is for you to have the rubric in your hands. This is what's used to grade CERs, not just by me, but by anybody. So they're usually graded on a scale of 0 to 2. The 2 column is obviously the ideal. So this is what you're shooting for. Your claim should answer the question, and it should be accurate, and it should be based on your data, which is your evidence. Your evidence should cite data and patterns within the data and uses labels accurately. In other words, if you're citing actual numbers, make sure that you have the units and all of that appropriate. Also, whatever vocabulary you use in here, it's important to use it. Use vocabulary that's appropriate to what we're talking about. Your reasoning needs to cite scientifically accurate reason. If there's like a scientific law or a theory that's involved, make sure you mention that and use it correctly. But this, again, shows that you understand the concepts involved. Now, a rebuttal, we don't really do that. So for right now, you don't have to worry about this too much. But this can be where somebody's responding to it, or you're providing your own rebuttal where you're kind of arguing with yourself. So for right now, you can just ignore this bottom part. Okay. Right now, you're mainly focused with these. So I hope that helps. We'll continue to practice. And if you have questions about it, please let me know. Come by office hours, ask me on GoGuardian, whatever makes sense to you. Have a great day.